Yeah, it is live. Yeah, it is live. So, okay. So good afternoon all. Today, welcome for this third lecture series of the third lecture of the lecture series Atmospheric Dynamics and its Applications to Climate Sciences. Today, the lecture will be delivered by Dr. Akhilesh Mishra from scientist NCMRWF. And the topic is vector equation of motion in an absolute and rotating frame of reference. Before we start with the lecture series, I would request AVM retired Professor Ajit Tyagi sir, who is President SAMA, to please deliver his welcome address.
Rohini, thank you so much and very good afternoon to all participants, organizing committee members and our esteemed colleague, Dr. Kyan Lwin U from Myanmar. In the series of our online lectures, we started with atmospheric physics, and even at that time, the need to have an online series on atmospheric dynamics was felt. It is so important. We're talking about weather and climate services and forecasting. It is the basis of that is atmospheric dynamics. So I'm very happy that we have now launched this program and it has been well received. And for understanding atmospheric dynamics, to know about it, we need fundamental equations, basics of mathematics, of which I'm really happy that organizing committee has planned basic lectures of this. The one was delivered last week and it's followed by today's lecture by Dr. Akhilesh. So this is very good to provide many of our participants who may not have basic knowledge, or even those who know, it is good to revise and update themselves about it. As far as Akhilesh is concerned, he's a part of our family only of SAMA. So we are very happy to have him to deliver this important. And he is one person who has, I think, entire spectrum which we talk in meteorology, right from the basic academics to the research to the operations. So his experience, both national and international, is wide ranging, and I'm sure he'll put that knowledge across in this lecture for the benefits of our participants. And really, and once again, Rohini and team, really thank you for organizing and conducting this series very, very efficiently, effectively. We have good participation, and the feedback which we received in yesterday's last lecture is very, very encouraging for all of us. And I request all participants to take interest. This is I think, if you pick up this topic, whatever of your interest, out of these 2026 lectures, it will positively help you in whatever you are doing. So please take interest, and I'm sure you will benefit. And even after the series of lectures, these are available on YouTube. So you could revise them, update yourself, and I'll request all our resource persons to guide you if there is any need about to further you want to learn about these topics. So once again, thank you, Akhilesh, for agreeing to deliver this lecture today, and I'm sure it will benefit all the students, and they will actively participate in the question and answer session, and wish you all the best. Thank you.
Thank you, sir. Now I request Dr. Lakshmi Kumar to please give the introduction.
Okay, thank you, Rohini. So on behalf of South Asian Meteorological Association, I'm very happy to introduce today's speaker, our Dr. Akhilesh Kumar Mishra, so who is going to give the lecture today. So Dr. Akhilesh Kumar Mishra currently working as scientist in National Center for Medium Range Weather Forecasting, Ministry of Earth Sciences, Government of India. Dr. Mishra's research interests are unified model, seamless prediction, very high resolution regional ocean atmosphere, wave coupled modeling for extreme events, NEMO, ORCA, and hybrid coordinate ocean model, intra-annual and decadal variability of ocean state, ocean modeling, and monsoon dynamics. Dr. Mishra received his PhD from Indian Institute of Tropical Meteorology, IITM, Pune, on numerical modeling of upper ocean dynamics in the year 2008. Later, Dr. Mishra worked as associate professor from 2017 to 2019 in Amity University, Rajasthan. And before working in Amity University, Dr. Mishra worked as associate faculty at the Florida State University, USA during 2011 to 2017. So Dr. Mishra received several awards such as Ministry of Earth Sciences Award for excellent work as official language, Hindi as official language, nodal officer of NCMRWF during the year 2021 to 2022, and courtesy scientist, Center for Ocean Atmospheric Prediction Studies, Florida State University, USA. Since 2017, Dr. Mishra is a permanent invitee in Ministry of Earth Sciences, Monsoon Mission Scientific Review and Monitoring Committee. He has publications around 35 in reputed national and international journals. And to name a few, the journals such as he has publications in Journal of Geophysical Research, Atmosphere, Climate Dynamics, etc. And moreover, he is the author of several reports and several book chapters. So with this brief introduction, I invite Dr. Mishra to proceed for his talk. Thank you.
Thank you, Dr. Lakshmi Kumar. So now I request Dr. Akhilesh Mishra to please.
Thank you. Thank you very much, Professor Lakshmi, Professor Rohini, and Tyagi sir. It was so nice to, getting back to something like this, and especially when the organizers asked my alma mater. One correction in my introduction. I think my PhD is not from IITM. My PhD is from Pune University. IITM does not award degree. So it is so good to come back to Pune University's event, and even if it is online in collaboration with SAMA, it is a pleasure to come and interact on such an important topic. And as I remember, Tyagi sir, when SAMA started, and our whole intention was to do the outreach and educate people about atmospheric science and meteorology, and the biggest beneficiary is the student and community working in the atmospheric science, and I hope they have all getting benefited. So I'm going to share the screen, Rohini. Please let me know if my screen is visible.
Yes, it is.
Is it in?
Yeah, we can see.
Full screen?
No, not full screen. Now, yes, yes.
Okay, okay. All right. So as I mean, a lot of good words were put for me by Tyagi sir. I hope I would try to justify all the good deeds he had and what nice words he has said about me. My experience in this field of atmospheric science, and especially numerical weather prediction, is very limited compared to what Tyagi sir and other great people in SAMA are associated with. But whatever little I know and whatever little I have experienced in last 20-25 years, I would try to share in next couple of minutes. What is very good to before delivering this lecture, I was going through last week Professor Vaidyanath's Professor Vaidyaray's lecture, and he has nicely put a lot of things which are basically covering the background of this lecture, and all about the different kind of forces in atmosphere. So instead of, and I was given this task of explaining this just equation of motion in two frames of references. So I thought I would take some time out, and couple of slides I'll show about the application also as well. Where do we use these equations, and what better than the place where I am working, India Met Department and NCMRWF, which is an operational weather forecasting agency for India. And as I just giving a brief introduction, Ministry of Earth Science, I'm actually working with Ministry of Earth Sciences, which has 10 centers spread all over the country. And these are the centers working in different areas of atmosphere and ocean sciences as well as earth sciences. And ours is the National Center for Medium Range Weather Forecasting. The center was started in 1989 with the first supercomputer, which was purchased by Government of India at back then. And as you can see in the right picture, that the Cray machine, which was being dedicated to the nation by then Prime Minister. And left side, you can see that if you're visiting happen to be in the Noida and India, please visit our center. This is still one and only piece of Cray machine which was delivered. Even Cray does not have this machine. So this is some kind of memory and some kind of showcase kept as NCMRWF. And please, that shows our history, that shows our the progress we have made during last 35 years. And this is, as I said, the supercomputers are the backbone of numerical weather prediction, and especially high performance computing is very much required when you're going for high resolution computers, high resolution modeling. And you can see this table shows how over the years India and especially NCMRWF has made progress in computing facility, and that is being translated in some kind of model improvement, model resolution, how we have come from 250 kilometer grid resolution model in 1988. Now to 2024, we are running 12 kilometer global model, 12 kilometer and jumble model, and 4 kilometer regional model over India. So this is where this is what the status is. As of now, we are upgrading our existing 2.8 petaflop computing facility to 8.4 petaflop versus Arunika. Recently, Prime Minister has dedicated this machine to the nation, and the machine is already going through all the test phases, and hopefully by a few days we will have operational runs going on these machines. Anyway, so just a little bit about NCMRWF. What we do, this is a seamless prediction system of National Center for Medium Range Weather Forecasting, and it runs various models at a various resolution and various time and space. 330 meter Delhi model, starting from 330 meter Delhi model to 60 kilometer global coupled model for seasonal to sub-seasonal prediction. And we do all kind of data assimilation, the latest data assimilation, and I would say the advanced data assimilation, which collects data from all over the world and assimilate in our modeling system to improve the prediction. So without indulging much more time into this, I think I would just give a little more background. What are the NWP models? So these equations, use of equations can be justified. So especially for the benefits of the students who are joining from different parts of world, NWP models are essential tool for forecasting weather. And the numerical model is a set of computer programs designed to simulate a real system. In our case, we are more interested in weather and climate. So here it is, weather and climate, you can say. Equations basically are following the laws of physics and the mathematics, and using latest advanced computing softwares are used to simulate the changes in the atmosphere, and that gives you the future state of atmosphere, whether whatever time scale you are interested in. Just a brief history. It was not a very old area. I think it is chalked out from the physical sciences 150 years back, and then 120 years back, and then slowly we have made some steady progress, especially with the advancement in the computing science, advancement into the observational networks. So we have made a lot of progress, and just to let you know that the first successful dynamical numerical forecast was made by von Charney and Newman, and it was in 1950. So where do we use these equations when we are discussing about the equations? I think in last lecture, Professor Somnath, those who have attended, has explained different kind of forces, in atmosphere. So these forces are then leading to different equations, so that the number of equations are then being used for, derive the future state of atmosphere, using time derivative and differential methods. So these equations are basically solved on a globe at a different grid point. So how do we define grid points? The whole globe, you can see here the right side, whole globe is divided into as a mesh different grid points. Of course, different kind of models are there. This is just one example of grid point model. There are spectral models as well, which are not using grid points, but this is what I hope the pointer is there. Yes. So this is just one example how these grid point models are used. And if you zoom in this grid, and you can see the equations are solved at all these dots, all these grid points. So all these equations, there are a lot of equations there. One of the equations which I will be dealing is the equation of motion today, which I will explain in two different frame of references, and how these equations are basically derived, and how these equations are basically solved to get the future prediction. And what we finally output is this. What you're seeing is this is what we are producing every day. This left side is your analysis. Analysis means once you assimilate all the observation into the model. So this is kind of, because we don't have observation on each point of the world globe. So what we do, we assimilate the observations in the model, and the model, the 6 hour or 9 hour forecast is considered as the best guess, and then this is called analysis. And there are forecasts as well. You can see this analysis compared to at the same time, the valid forecast. This is what you're seeing: outgoing long wave radiation, 18-hour forecast on the right side, and the same valid at the same time on the left side. So this is just an exercise. We are also predicting in other variables. This is what you're seeing is the precipitation rainfall forecast for a particular day. On left side you are seeing day 5 forecast. On the right side you are seeing the centered on the India, the forecast for next 10 days. So the whole idea to give you this background is that these equations which we are going to discuss in next few slides are, I'm sure they are going to be very, very boring, when especially people who don't like mathematics and who doesn't probably may not follow 100%. But just to tell you, there's a very, very useful tools. They are very, very important part of numerical weather prediction, and they are the one, because of those equations we are able to get these timely and accurate forecasts for weather and climate. So let's get back to what I was asked to discuss today. And so let's first see what is the atmosphere equation. What is the equation of motion? And equation of motion, when I say you say it can be on any from reference. People in mechanical engineering, people working in the civil engineering, people working in the chemical engineering, they are using in a different way, in a different kind of aspect. But we meteorologists use it for the purpose of atmospheric calculations and atmosphere, to understand atmospheric movement and motion in the atmosphere. It describes the movements of air parcel in the atmosphere. So considering one air parcel of atmosphere, how that moves following the laws of physics, and especially the second law of Newton's second law, which is basically nothing but force equal to mass into acceleration, which is basically used. And when we additionally use the Earth's rotation and friction, then it becomes the complete equation. But what I'm going to start with, basically what is without rotation first, and then we will see how rotation is added into it. And why the different frame of references? As I said, an absolute frame of reference is a fixed in space. When this is something which we all know, Earth is not fixed, it is rotating on its axis. And when somebody is standing in the atmosphere, looks from the space to Earth, they can observe that Earth is actually rotating. So any movement, any motion which is happening over the Earth should also consider that the spin and the rotation of the Earth as well. So understanding these motions in both frames of references are very, very crucial and important to make the accurate weather prediction and climate modeling for the climate perfect as well. So just once again, I'm just tabulating. Many of these things will probably be in the following lecture. Some of the things will come, you have already been explained, but these are the basic set of governing equations which constitute numerical weather prediction model. So there are three equations of three component of the wind which they deal with. They are based on second law of Newton. Newton's second law, and they're basically following the conservation of momentum. And there are two equations, one for air and one for water, because atmosphere has a moisture, humidity, so that can be considered as mass as well. So two equations for the conservation of mass, one for the air, as I said, and one for the water and humidity. And then one equation is for the conservation of energy, which is nothing but the first law of thermodynamics, and one is the gases equation. We all know PV equal to nRT, which is relationship between the gas volume, temperature, and physics. So coming back, I'm not going to the focus of this talk is just the first one, conservation of momentum, and especially equation of motion. And I'm sure the coming lectures, you will get the details of all other basic governing equations as well. In previous lecture, Professor Somnath has already explained what are the fundamental forces in the atmosphere, especially pressure gradient force and friction force, which this and Coriolis force he has already explained. But I'm going to start. I'm not going to repeat that. But whenever I'm going to use in next couple of slides, I would probably refer them as a I hope you are following that, and I hope you will follow those. If you have not followed that, please feel free to ask me after the lecture. So this is the equations governing the laws, atmospheric flows, and there are two words you would hear in the Lagrangian, and there are two type of basically words you probably see, Eulerian and Lagrangian. So when Lagrangian is something where you have this rotating frame of reference, where the motion itself is moving, the earth is moving. So Lagrangian is used when there is the motion, the body itself is moving, and the Eulerian is something when you have something in the fixed space and time. So the equations governing large-scale atmospheric motion will be derived from a Lagrangian perspective, that is from the perspective in a reference frame moving with the fluid. So here, as I said, this is most appropriate for Earth's rotation, and especially for atmospheric flows. The Eulerian viewpoint is normally the one we are concerned with. That is, what is the temperature or wind at a fixed point when we are doing at a particular point fixed and the Earth's surface as a function of time. That's when we go for the Eulerian. But the Lagrangian perspective is useful for deriving the equations and understanding why Eulerian winds and temperature evolve in the way they do. So let's say the material derivative is d by dt is the rate of change of field following the air parcel. Let's say the air parcel, considering one particular point, let's say very small a small amount of air, which can be considered as the separate from the surrounding, and how the change in the with the time. Let's say, for example, here temperature is taken one example. So how with the time this temperature is changing. So there is total change, which is material derivative. There is some local change, and then there is some advective change. There is a wind component here, which takes care of the advection. And this is we all know, this is, if you know the calculus, the dot product LT. So this is where these terms on the right hand side is Eulerian derivative. That is the rate of change at a fixed point, this one. And the second term is the advection term. That is the rate of change associated with the movement of the fluid. So because this wind vector component is there, wind component is there, and through the background temperature field. So if the material derivative is 0, suppose it is 0, then the field is conserved following motion, and local rate of change is entirely due to advection. So that means, if considering that there is no surrounding things, whatever is there, then whatever changes are happening in temperature is just because of the advection. Basically, let's say there is a air parcel which is moving from one place to other. So if it is conserving there is a term you would see in later adiabatic, diabatic. Those terms will come as you come to the next lectures. So in that case, the change in the temperature is going to be because of the advection from one place to other. So this is just basically one equation which is a basic. And let's say when deriving the equations of the equation of the motion from a Lagrangian perspective, we will consider fluid element of the fixed mass. But where volume may change, and it is therefore necessary to consider the material derivatives of the line vectors. For example, let's see this picture. For this, there is a, you can see these two dots. Let's say at t equal to 0, there is a something is in the space staying here, and the velocity field is like this. In the lower portion of this this object, the winds are slightly slower, whereas in the top portion it is slightly faster. So as you see, after t plus delta t, let's say suppose after at t equal to at certain place, time and space, this is at this time, but after delta t time, it reaches here because of the winds, stronger wind on the top portion. It is tilted towards, it is moving more faster compared to the earlier. So this is just a demonstration which we will use into the equations in coming ones. So this line element could represent, for example, the side of an infinitesimal fluid element, considering that. And so let's say if the line element is connecting to that, connects 2 points that are moving with the velocity field of the liquid, it will change its position and orientation as well over the time. So the orientation, the line element at time t plus delta t is given by this delta r is equal to t plus delta t equal to delta r at t plus the v multiplied v and vector v and r plus delta t at delta t. So this derivative is, then you can transform this equation into this. You can take the r at t plus t minus r at t, time equal to 2, difference of this divided by delta t, time difference. And then on the right side, it will remain the same because you have taken delta t divided this by delta t, and this becomes delta v by d by derivative and delta r. So the left hand side is just a material derivative of the line element. So we have we have the important result that says d by dt of del r equal to del r into delta t. So where v is nothing but dr by dt. So the different shear terms can affect the size and orientation of the line element. So what we have seen in the previous figure, the line element has is experiencing two different kind of wind at two ends. So that is actually creating this change in the orientation. And for a particular dimension q, we have the general result that says 1 by del q d by dq of dt, and then del by del q dq by dt. So the equations that govern the atmospheric flow will now be derived from the Lagrangian perspective. So far we have discussed only the Eulerian, and these are the mass conservation, basically following the mass conservation, momentum conservation, and energy conservation. So these three are the basic, as I saw you in the earlier slide. My focus is only in the momentum conservation because that deals with the equation of motion. Others are basically dealing the other equations as well. So conservation of momentum, let's say considering the infinitesimally small air parcel of constant mass delta m with the variable volume. Let's say volume is variable, we are allowing volume to change, and density. We want to know how the momentum of the parcel will change. The rate of change of momentum will be equal to the sum of the forces acting on the parcel. As I said, I mean probably in the previous lecture, Professor Vedra has explained very nicely with showing the three-dimensional picture how different forces applying on a atmospheric parcel are resulting in a pressure gradient force. So this gives you the forces acting on parcel. So it is nothing but what we have discussed. F equal to ma, force is equal to mass into acceleration. What you see here, m is, this is very small amount of mass. D by dv by dt is nothing but acceleration, change in the velocity with the time, acceleration. So mass into acceleration is your force. So this is the basically thumb rule of, as I said, Newton's second law, and our equation of motions are derived following this law of physics. It's simply adding the terms what we are experiencing in the atmosphere, what air parcel of the atmosphere experiences. That's what we are going to have. That's what's going to be considered in the coming things. So anyway, so there are several forces we may have to consider when examining the motion of fluid elements in the atmosphere or ocean. So please also note that these are equations and laws are not only applicable to the atmosphere. There are also similar laws, same physics, and the mathematics is applied in the ocean as well. The only difference is compared to the ocean, atmosphere, ocean is much more, the considered is much more fluid, because for the simplicity, for the sake of simplicity, atmosphere is considered as a fluid motion. The fluid motion, fluid dynamics, laws of fluid dynamics are applied, which are much more suitably applicable in the ocean. So that's why predicting ocean is easier compared to the atmosphere. Atmosphere, a lot of chaos. Atmosphere has a lot of uncertainties, and although number of observation in atmosphere are way more compared to ocean, but predicting ocean is easier because it follows the considering the fluids and all those things. Observations are less relatively. Anyway, coming back to this equation. So what are the forces? So these things Professor Vadra has explained, so I'm not going to go to the details of these things, how they have come, but if anybody has question, please feel free to ask me after the the presentation. But I'm just going to summarize them in just a few lines. So here, as you can see, pressure, this is a pressure gradient for, consider the vector area element whose normal vector is given by ds in the figure 2, which we have seen earlier. The pressure acting on this area element is df by p, dfp, and this is nothing but minus pds. This is, we have already seen pressure gradient for integrating over the surface area. The element gives fp is nothing but integration of, by integrating this against the surface, which from the divergence theorem can be written as which this expression. So which is you have all you are all aware. Gravity, we all know there are the mass attracts mass. So we all know that considering 2 g MEM by r square, which Professor Vadra has explained. So I have simplified it here because it is for the unit mass. So considering it, if you see here, fluid element in the geometric height coordinate, it becomes Fg equal to nothing but del mg, which is often written as nothing but del m and delta phi. Phi is nothing but geopotential, gz, which is geopotential, and g is the acceleration due to gravity, which is for many purposes constant. We all know that g equal to g is constant. The reason for writing it in this form is that we may consider flow in different height coordinates. Sometimes it is pressure, sometimes it is sigma, sometimes it is the altimeter z coordinate. So commonly pressure basically we are going to use, we will whatever we are going to refer here. Thus a particular vertical level in our coordinate system may not necessarily be horizontal, and there may be component of gravity acting along the level. So this is something which we all have probably in previous lecture Professor Vadra explained, but I'm just going to see one more important component, the viscosity. So viscosity is the fluid, the nature of fluid nature of the liquid. That viscosity arises from the shear stress between layer of a fluid and that moving with the different velocities. The viscous force per unit mass is often Fv equal to mu del square V, where mu is the kinematic viscosity, which you can read into the Halton's book, which I have referred into the suggested reading as well. For atmosphere below 1,100 kilometers, the viscosity is so small that it is normally negligible, except for within a few centimeters of the Earth's surface, where the vertical shear is very, very large. So this is, there is a one the Reynolds numbers which we will probably come across in coming lectures. This is a measure of viscosity. It tells the importance of viscosity. It is the ratio of inertial force to viscosity, and in most of the atmosphere, the Reynolds number is large and viscosity is relatively unimportant. So anyway, so these terms we ignore. We sometimes, as per the convenience of the calculations, we ignore something. So our rate of change of the momentum equation is given by the sum of these forces. So dividing through by delta m, because it is per unit mass. So given as an expression by the acceleration of the fluid parcel as an initial reference frame. So this becomes, equations become this, where this is pressure gradient, this is your basically g, the gravity, and this becomes your friction. If fluid is at the rest, then we have hydrostatic balance. So that is another thing which you will probably see. So now up until here we have seen Eulerian. Now we'll go to the Lagrangian. So now what happens when the frame is rotating? We have not considered anything other than pressure gradient, force, and gravity. So earlier we have considered that rate of change of momentum of our fluid element to the sum of the forces acting on the fluid element, but that only applies when we are considering motion in an inertial frame of reference. Normally, when we are examining atmospheric motion, we are not looking at motion in an inertial reference frame. Rather, we are concerned with how the atmosphere is moving with respect to the Earth's surface. That is in a rotating reference frame. We therefore have to take this into account when determining momentum balance. So, for example, consider a parcel of air which is at a fixed position with respect to the Earth's surface. The Earth rotates with the angular velocity omega, which we have referred as a vector. The position, if you see on the from the top of the Earth, from the northern hemisphere, it is moving anti-clockwise. From the southern, it is clockwise. The position of the fluid element does not alter in the rotating reference frame of the Earth, but from the point of view of an observer in the inertial reference frame, the position vector will move as it rotates with the Earth. So the rate of change of the position vector as viewed from the inertial reference frame, somebody standing in the space, somebody looking from the space, may see with this equation, can be represented as this equation, del dr by dt equal to omega multiplied by r. So this is basically coming from this. R is here, omega is this, as you can see, this is a rotation, omega is Earth's rotation, and you can see here this is illustrating the Coriolis force, and I think Coriolis force also Professor Vadra has explained, but I'm going to show you how these are coming into the equations, how they are changing the vectorial form of the equation of motion from a absolute frame to a rotating frame. So this is just showing you the angular momentum of the Earth's rotation and how these are going to change. So if this is the interesting part, so if the air is moving, so what is going to happen? What the air parcel with the moving air velocity will become, this is inertial, and this is dr by dt, inertial, and dr by dt at reference, and rotating plus omega r, or omega cross r. So that is the sum of the velocity in the rotating reference frame and the velocity associated with the movement of the reference frame. So this is just but the total of these two. So if we say vi equal to vr plus this is just nothing but velocity. These terms are basically velocity. So if we now consider the rate of change of the inertial velocity in the inertial reference frame, it will be related to the rate of change of the inertial velocity in the rotating frame, reference frame, by the same transformation. That is duvi by dt. It becomes inertial frame of reference becomes rotating frame of reference change, and then this term. So, and combining these equations, if you see with the 10, then we can write this equation like this. So replacing v and everything, whatever defined. So this equations becomes dv by dt inertial equal to dv by dt rotating plus 2 omega into vr into plus omega into r. So this becomes, what is this? This is your Coriolis term. This is your centrifugal term, which will come anyway. Where second and third terms in the right hand side is the Coriolis force and centrifugal force respectively. Then this is arriving because of the rotation of the Earth. These are fictitious forces introduced by the fact that we are examining the motion in a non-inertial frame of reference frame. So let's go to the next equation. So these two forces, additional forces, then you have, instead of having a absolute frame of reference, we are going to the rotating frame of reference. So these two players come into the force, and these two forces which are considered negligible earlier. So now these are centrifugal force, which can be written as omega into cross r, where r is the component of the position vector that is perpendicular to the axis of rotation, which we have seen in the earlier figure 3. This can be rewritten as omega dot r omega plus this, and then becomes RHSI becomes omega square r. So this can be written as the gradient of a scalar potential. This is nothing but del c, where del phi c is nothing but omega square r by 2, 1 by 2. Therefore, the centrifugal forces often combined with the gravitational force in the previous equations, and together they become together they are addressed. But for many purposes, the centrifugal force is small and can actually be neglected. So you probably, if you see the full equations, you will see, but sometimes for the purposes of applications, we sometimes for the to reduce the complexity in the computation, we sometimes ignore. And Coriolis force, I don't have to tell again, but the Coriolis force can be thought of in terms of angular momentum conservation. For example, consider as an air parcel starting at position 1 at the low latitude in northern hemisphere, figure 3. Suppose now a force acts to shift that air parcel poleward, and this probably has there is a YouTube video, you can see this. You try to rotate a paper on the desk and try to move, try to write draw a line from using pen away from you. And after, if you're rotating it to anti-clockwise, you will see it is turning towards right. Your line is nothing but it is turning right. If you are rotating your paper on the clockwise, it will turn your line on the left. So that clearly gives you that's a demonstration how a Coriolis force is affecting, impacting, changing the direction of the force, right side in the northern hemisphere and left side on the southern hemisphere. So this is just a demonstration. Many students can try on on their own. You just Google on YouTube, you probably see how to do it. You can experience on your own. So coming back to the equations, this is if you add all these three terms, and in the inertial reference frame, what is normally take care of motion in rotating reference frame. So considering those two, dv by dt in rotating frame of reference, rotating plus 2 omega vr, r is rotation actually, and this is nothing but your pressure gradient. This is your basically considering the gravity term, and this is your friction term. So as we can clearly see again here, this where we have either neglected the Coriolis form, lumped it in with the gravitational potential. We assume we are examining motion in the rotating reference frame of the Earth. So to conclude momentum balance in the rotating reference frame of the Earth, where pressure, gravity, viscosity, and possibly other frictional forces are acting, is given by this. So this is one form of things. Certain components are, again, as I said, neglected. Sometimes they are considered, sometimes they are approximated. So this equation itself tells a lot of approximation are done. So once again, just I'm trying to put it in a simpler way. Equation of motion has these forces, real or apparent, you can say. So pressure gradient force is nothing. I can clearly see this expression. Viscous force, viscosity, we have already explained. As I said, G, your gravitational force, which is in between two bodies, G m by r square, where the body, the force, the mass of your air parcel is negligible. So this is gravitational constant, where the centrifugal force we have already explained, derived. Coriolis force we have already seen. So, and all this gravity force. So acceleration is nothing but the gravity. This is again putting into the the F equal to m into a, the pressures, gradient force, Coriolis force, and frictional force. So this the arithmetic sum of these, this equations is in the vector form. When you just consider the horizontal component, so you actually ignore the vertical components, only horizontal components. So this equation you can write in this way, where x is, it can be at x or y instead of x or y, zonal or meridional. And as I say, just giving you one example, horizontal momentum equation from things. As you can see, there are two pressure, you can say two isobars, 1005 millibar, 1000 millibar on the surface of the, it's not vertical by the way, this is at the surface of the Earth or any surface, plane surface. So obviously the pressure gradient force will be from high pressure to low pressure. So you can see the direction of the pressure gradient force. Coriolis force in the northern hemisphere will be on the right side of the pressure, your movement, and the wind should be in this direction, but parallel to the isobar. But that's not the actual case. In reality, the frictions are coming into the picture, which takes it into the slightly left. So they basically, the actual winds are blowing from high pressure to low pressure. Otherwise, this in absence of frictional forces, these winds will never stop. They will blow, they will float along the isobars. Anyway, so this is just one example how these equations are basically used, how these equations can be interpreted, how these equations are basically put into the model, and what are the, I mean, this is just a simplest form what I'm showing you. There are a lot of components, lot of other forces into the equations, many of them which we ignore for the computational simplicity, and many of them which are being basically considered assuming the complex nature of the atmosphere. So just to summarize, equation of motion, which I'm just summarizing, this is probably my last slide. I hope I'm not taking much time. Equation of motion, which can be represented in various forms based on frame of references, coordinate systems. Sometimes, the different kind of coordinate systems are using different kind of, the be it a rotating frame, be it, whatever pressure coordinate, a sigma coordinate, all these coordinates and their uses. In the meteorology atmosphere application, it applies to air mass parcel following the Newton's second law. Can be defined as acceleration of parcel of air in the sum of the force applied to the parcel. A set of this is, by the way, the definition of this is how it is defined in the AMS, American Met Society glossary. You can Google it, you can get this equation. This is same which we have derived on the earlier pages, and you can see that this is acceleration term, this is basically your Coriolis term, this is gravity, this is pressure gradient, and this is frictional term. So this is a complete equation, and it is defined a set of hydrodynamical equations representing the application of Newton's second law of motion to a fluid system. The total acceleration on an individual fluid particle is equated to the sum of the forces. These are the sum different forces acting on the particle within the fluid, written for a unit mass of fluid. By the way, these are all you might be seeing that where is the mass is this is for unit mass anyway. So divided by mass, so all divided by unit mass fluid in the motion of a coordinate system. It depends, these equations what you see here, you may say in a different kind of structure depending on what coordinate system you are seeing, fixed with the respect to the earth. The vector equation of motion for the atmosphere is like this. So where all these different things are there. Suggested reading for my side, there is a Halton book, Introduction to the Dynamic Methodology. Please follow. If there is a lot of interesting exercise, lot of interesting examples are there and very nicely written. If you somebody wants even simpler, there is a Haltner William. But if you have slight interest in mathematics, then probably you follow the second book. The first book has less mathematics compared to the the second one, but the second one is a very interesting read. And if you are just want to read as a story book, I think I would say for many purposes, Halton's book is most referred book for dynamic methodology and to make you better understand the atmospheric dynamics. And that's all from my side. Thank you very much. I hope I did not take much time, but if there is time left, I'm happy to answer questions, any doubt, any query. Thank you very much.
Thank you, Dr. Akhilesh. Though this is there are a lot of equations involved, and I think it is really slightly tough for the participants, but yes, it was very nice. Can you unshare your screen, please?
Oh yeah. I'm trying to stop sharing. Yeah.
So we will just have a quick photo session before we go to the question answers session. Yeah, I would request everyone to please switch on their cameras. Tyagi sir, Lakshmi Kumar, Mohan Kumar, Kya Lingu, Vishal, please switch on your camera. Dr. Lakshmi. Dr. Lakshmi is not there, so okay. Vishal, did you take? Okay. More? Just 1 minute more. Dr. Lakshmi? Done. Okay. So I would request now Dr. Mohan Kumar to please moderate the question answer session.
Thank you so much, Dr. Rohini, and of course, to the research persons. So I have seen there are many questions in the Q&A room. For the first question is from anonymous attendee. What are the steps or method for upgradation for good or accurate forecast?
So See, the forecast system nowadays actually, or maybe 30, 40 years back, is not, it is basically two components. One is assimilation and then one is forecast. So first of all, you should have a good model which can issue good forecast. You can rely the forecast. It should have the latest advanced physics considered. It has latest the mathematical calculation, least approximation, least assumptions should be there, which is not possible practically. You can never have a perfect forecast system, by the way, just to tell you. But we should always go for the superiority, go to the better ones. And assimilation is a very, very important part. See, numerical weather prediction is a initial value problem, and climate modeling on the other hand is a boundary value problem. So if you have a good assimilation system, if it has a very good model, it will assimilate the observations and it will provide the better analysis. So better analysis will lead to a better forecast. So to answer your question, so what is the method for upgradation for a good accurate forecast? I would say you should have a very, very good model and equally good assimilation system, because assimilation also is happening in a different kind of assimilation: 3D variational data assimilation, 4D variational assimilation, ensemble Kalman filter, and many various complex mathematics is involved. So having a good assimilation and forecast system will certainly lead to a better forecast.
Thank you so much for your very prudent answer. Actually, it is not a one step forward solution. There's lots of dependency.
Correct.
Exactly. So next question is related to the wind or motion. Wind or motion is the most important element in the model to derive all other phenomena or element.
So that's very interesting. See, I don't know. There is a movie. Hollywood has a movie called Meteorologist. I don't know. Maybe you watch that movie if you find somewhere. It's probably free. So the weather system in higher altitudes, upper, beyond tropics, probably for them it is true. Wind is driving the weather on those areas. That's why the forecasting weather is far more easier compared to tropics. So tropics, we have a additional term. If you know the wind in extra tropics, in higher latitudes, you can certainly forecast weather easily. But if you're in tropics, there are additional term which is basically in our equations we probably are not able to parameterize properly, is a convection. Convective terms. So that creates problem. That probably leads to some kind of complication. It is not as simple as the forecasting weather in the upper latitudes. So that is why if you see in the winter season, especially even in tropics, the winter season forecasts are better. But as the summer comes here, the convection comes into the picture, and then only wind is not sufficient. We should know the wind plus moisture plus other things as well. So a lot of complications are there. Yes, wind is very, very important even when the when the summer is there, but wind alone cannot give you all answers. Thank you. I hope I answered your question.
Yeah, exactly. Thank you so much. Very relevant and very confident answer. And I have seen another questions. As India has different geography for all different states or meteorological division. So while running model for forecast, we should run model for different meteorological division or whole India. In both cases, the forecast will be same or it can be vary.
Interesting question. Probably I've never thought of this way, but yes, if I have enough computing power, I would try to run for a different region. So, but yes, one thing what you probably have not thought, that if I am running model for India, it is also getting air from surrounding neighboring country. It is also getting moisture, air, wind, everything coming in the neighboring country. So if I am ignoring that, so how the model's forecast is going to be. So that's why many people don't rely on don't trust on the regional model, although I'm not in that favor. Regional models are equally good. So what you are suggesting, we should use a regional model, very, very high resolution, hyper zoom at a different climate regime in India. Well, if somebody wants to do that research, it's fine, but our global models at current stage are capable enough to resolve these climate zones because different boundary conditions are provided. Model knows when there is a hill, mountain, where there is a the desert, where there is a the oceans. So those boundary conditions are provided. So that probably takes care of these different geography. But yes, that experiment what you are seeing is a very good exercise for academia and for research. Somebody should certainly take and see how different it is. But as of now, as I said, our existing models have no problem in simulating weather and climate, addressing the geography. So that's a boundary condition, because lateral boundary and different boundaries can be properly given to the model. Model will know what kind of geography is there. Thank you.
Excellent. And in addition, I think nesting procedure is also one solution, right?
Exactly.
Excellent. One question from Didulanga Osid. We have seen many times that weather prediction gone wrong within few hours. My question is, why is that, and what are the facts that affect to change of these kinds of predictions?
So, Didulanga, I think I would say that is why forecast is done continuously. You see, if forecast would have been we have been so confident in our forecast, we would have forecasted today and then got relaxed. But every 6 hours we are forecasting. So as I said, numerical weather prediction is the initial value problem. So when what happens when the initial condition goes wrong? Suppose our model is not getting the observation in right time. So some observations are missing. We are not getting. By the way, we are running within 30 minutes of observation. The data should be received to the operational center. And you won't believe, we were having discussion yesterday. By observations are taken at 8:30, but we start assimilating at 7:30. So for 1 hour observations, we don't receive in the operational time. So that is why we run later on, because we have to issue the forecast to IMD India Met Department so that the forecast can be sent to public in the timely manner. So first and foremost thing is, forecast is very, very sensitive to the observation, to assimilation. So if the assimilation system is missing some observation, it will lead to the wrong forecast or error in the forecast for sure, no doubt. But that's why I said you should always look like, for example, you are interested in 3 days weather after 3 days at your place. So you should see today, and it's not that you should just see and believe. You should keep on seeing it, because we are issuing forecast every day, twice, thrice. So you should keep on seeing is if you see consistently the same weather, that is what going to be expected. That's normal the case. But what you are saying, sometimes it goes wrong. Some extreme weather cases, yes, we may miss it. We may not get the extreme magnitude, but we certainly get the signal through our model. And for there, I think somebody will take lecture. I'm sure about that. Why these models have those limitations? Why parameterization and these problems? Approximation in the parameterization schemes leads to that errors. So that is why our models, none of the models in the world are going to be able to predict the cloud burst. But there are ways to fix it. Artificial intelligence, machine learning, people are practicing that, people are using that. Probably in coming time, we will be able to forecast that as well. But to answer your question, yes, predictions can go wrong. Prediction means it will go wrong. It can go wrong from 0 to 100%. But it doesn't mean that we should not rely on the forecast. We should continuously look for the forecast. We should regularly, if you are interested in a particular day or particular events forecast, particular day at particular time, please keep looking into the forecast, because several cycles of forecasts are issued in every day. So maybe our one initial condition was wrong, the other initial condition may be better, so that will issue better. By the way, impact of assimilation, certain observations, the impact of certain observations assimilation does not remain with the model 24 to 48 hours. After that, the impact goes down. So that's this is a very, very complex area, and a lot of people are working. I hope you would also understand after some time, or maybe you are understanding. So I hope I answered your questions. So the best solution is, you please keep looking forecasts, different cycles of the forecast.
Yeah, exactly. Actually, forecasters, meteorologists are doing a great job for the community. So within the time period, they are providing nowcasting, forecasting, everything. So I think people responsibility also to monitor the forecast within the time. Thank you so much. Another question is from Deshmukh. Asked, how does the Coriolis effect influence the ocean current?
So actually, yes, this is interesting. So ocean has different. Somebody, have you taken some ocean classes as well, Rohini? Is that plan? So actually, if possible, we can have a good class lecture. I didn't know, otherwise I would have prepared.
The
So
demand,
ocean also,
Maybe
ocean, yes.
sometime later it will be.
the demand came one of the co-organizers,
Mm.
but still it is not.
Yeah, it's pending.
No, it is interesting. It is very important question. Yes, it does influence, but there are different term for that, different ways to express that. And yes, it is very important. Of course, ocean fluid is also following, as I said, fluid dynamics, laws of fluid dynamics are applicable there as well. But it is a different amplitude and different ways to express that. There are there.
Okay, thank you. Actually, there is lots of questions. Many new questions are arriving. Another question is how this equation of motion differ for ocean system.
Yes. So Rohini, you have to plan for ocean. So it does. There is a so one see what happens in the ocean. Salinity comes into the picture. So when you are inside the ocean, you just assume that ocean water is your air, and you are a fish. Okay, instead of human, you are a fish. So then what variables we use? Salinity, temperature, and density. These are three most important variable. And the equations of states are derived, most of the equations are derived following the laws of physics, as we have seen in the case of atmosphere. And the set of equations are almost same. The only thing is the vertical coordinate is reverse here. You know that from top to bottom, it is from bottom to top. So there are certain very minor change, but the laws of physics and laws of thermodynamics, laws of the mathematics are exactly same. Fluid dynamics, laws of fluid dynamics are applicable. In fact, they are much more accurately used in the ocean cases. So yes, there are equation ocean models are written following those equations like atmospheric model. So certainly I would request Sama or maybe somebody from NIOT or somebody from Ocean Institute, or maybe Dr. Mohan himself
Yeah,
can
I was
host
trying to
this.
say that Mohan is there.
Yeah,
Mohan, you
who
can
better can organize next series of lecture in the ocean. So this is very important aspect. So certainly it should be addressed.
Thank you so much. Why the pressure gradient force and Coriolis force is negative and frictional force is positive in the equation of net acceleration?
Yeah, so it is all depending how you are because this following the Newton's second law, F equal to m into a. So if you change the side, it becomes positive and negative, and it is applicable to the body. So how it is affecting the body, so that decides the sign of any force. So the friction, which is basically slowing down, is basically that's taken into the positive because it's the other side of the equation. And when you take it to the other side, so signs are nothing but basically, as I said, when you're changing the
Okay,
sign,
great.
or because they're summing the equal to zero, that's the law. So anyway, so that's how it is. The signs are basically, you have to understand, you have to read that again, and you will understand basically the diagram, how these signs are decided.
Sure. Thank you so much. Questions from Milin. First, I appreciate your informative lecture. As it is already said that prediction when it comes to ocean is easier than that of the atmosphere. How does the model handle the air-sea interactions?
Okay, so very good question. So ocean, when I say easier, it does not mean all our ocean forecasts are right. Easier because state of oceans does not change that fast as atmosphere. So if you see SSTs, there are diurnal changes are very small. But if you go to the air temperature, diurnal changes are very high. So that is why when you want to forecast ocean, you don't basically, you are not interested in seeing into the hourly temperature in ocean. But unless your objective is something else. But in the atmosphere, you are certainly interested. Now, air-sea interaction becomes important because let's say even ocean remains at 32 degrees, but surface of the ocean remains at 20 degree, 28 degree, for example. but atmospheric temperature is changing from morning 16 degree to 35 degree. So just imagine what kind of sensible heat, latent heat interaction is happening at the interface of the ARC. So that's very, very important. So models certainly, what happens earlier when there were no couple model. So this atmospheric model was given in a constant SST. There is the SST was considered as a lower boundary. So lower boundary condition in the atmosphere was fixed. Now what is happening when you have a coupled model, which is a dynamical model, which is giving you every minute's temperature? So the ARC interaction, the fluxes between ARC are much more realistic compared to the previous cases. So that is why it is very, very important to use coupled model. Most of the leading numerical weather prediction center in the world, including ours, is now operationalizing the NWP model in a coupled mode, which will be issuing much more realistic forecast. But then again, as I said, unless you know the model properly, implementing as per the law, as per the rule, it should be coupled, but proper implementation, proper coupling is required. So we are testing that, and it is without properly understanding, if we couple it, it may lead to the certain wrong thing, but it certainly should improve the ARC interaction if you have a coupled model. So having an ocean model certainly helps in a whether it is a time scale of weather or time scale of climate. I hope I answered. I don't know why I went somewhere else. Probably I got emotional.
No, it's very relevant. I think you answered very elaborately. Of course, there is still many questions are coming.
Yeah.
Zosan asked, tropical region, for tropical region, which equation or approximation is more suitable or more appropriate?
I don't know what he referred to, Johnson. Which for tropical region, which
No,
equation?
yeah, he is asking regarding the what kind of approximation is more better for the tropical region.
What kind of approximation?
Maybe he is asking some combination of schemes or something relevant.
Oh, okay. So
I guess so.
See, it is. I don't know if you are asking about. There is one parameterization scheme. Lot of approximation is done. So I don't know. We have not. I think this the lecture was not covering that, but probably somebody will come. But here, if you see in the equation of motion, irrespective of tropics or extra tropics, the hydrostatic approximation is considered when the vertical component of the equation of motion is considered, the vertical movement is very small. So that probably is applicable to all over the places. Depending on model capability and your own computational resources, you can use non-hydrostatic or hydrostatic modeling. So for example, when you consider the vertical component of the equation of motion, you are adding one more equation into the computation. So because for example, we are considering it, we are not ignoring that. So that approximation.
Okay, that's great. What is the difference between geostrophic and? Okay, please continue.
Yeah, please. Done. Thank you.
Okay, so what is the difference between geostrophic and subtropic winds?
Geostrophic and subtropic. Okay, maybe Sharmaji, I think we have to go again and read the book. Geostrophic wind, as I showed that picture, it is just showing the parallel to isobar, which is ideally not happening into the atmosphere. Subtropic is the winds, blowing into the subtropical area. So it's just, if you want me to tell the definition, although there is no relationship between these two, they are the winds. Subtropical winds are winds, flowing on the subtropical regions. But geostrophy is something which is not a reality, and it does not exist. But for the mathematical calculation purposes and for the demonstration purposes, we tell students, we teach students, and normally we also study that.
Yeah, I think already many books are there, so
yeah,
they can get more.
I think coming lectures will elaborate this. This will be much more clear to them if you attend the future lectures.
And Gayantir from Sri Lanka asked, can you explain more about the two? Okay, thank you. Gayanti asks from Sri Lanka, can you explain more about two different reference frames, their effects on weather and climate?
That's very interesting question. So basically, this is much more related to my talk. So two reference of frames is one. Let's say I am standing in New Delhi, and I'm stationary. Okay, I'm not moving. I'm sitting in my room. But if somebody for example, I have decided to move, go from here to my office, which is around 10-15 kilometers. So I'm moving from here to my office with a 50 kilometer per hour speed. So I am considering my speed, okay, 50 kilometer per hour. But let's say somebody is standing in the International Space Station, or somebody is flying in the atmosphere, away from atmosphere basically, and they are seeing the Earth is rotating. I am also moving. So when the consideration of Earth's rotation is basically coming into the picture, so that's become the rotating frame of reference. Otherwise, it is stationary, which just to example I have given into my talk also. So the effect of weather and climate is very important. Without their consideration, you cannot, your many terms you will be missing. So without the consideration of rotation of Earth, you cannot, there is no day and night, first of all. That will also lead to that. And then that term Coriolis is very, very important. All the rotations which are happening, rotational, structures you are seeing, whether it is cyclones and, all these northern hemisphere, southern hemisphere, all the motions, trough, ridges, they're all happening because there are rotation. Earth is not, just stationary. Earth is basically rotating. Because of that, normal winds which should have been blowing from east to west are basically getting curvilinear, turn, and then they try to create certain weather disturbances. So these are very, very important. Sometimes they lead to weather disturbances. Sometimes they enhance weather disturbances. So they are very important.
Thank you. Thank you so much. Another question is, which type of force is highly affecting for the air parcel movement?
Pressure gradient force. So that's most important, the first and foremost. So the wind is blowing because there are pressure gradient force. So the magnitude, if you see the scale analysis, the first chapter, if you read the Halton's book, the very first chapter is scale analysis, which actually tells you which force is of which scale. So there you will see the most important force, most important the factor you can say is for the parcel movement is pressure gradient force, which is responsible for any air movement or any movement in the air.
Thank you. Next question is, which is the good method of data assimilation?
Of course, this lecture was not for related to data assimilation, yes, and I hope I am not an authority, but I can tell you the latest advanced data assimilation method used at NCMRWF is hybrid ensemble, hybrid ensemble, and 4D-var. So that's depending on which model you are using. Different models are using different kind of assimilation method. So this is what we are using, which is
I
latest.
I think exactly because of your affiliation, maybe he or she
yes,
asked this.
I understand. Probably I have shown some slides also. So curiosity, right. I understand.
So suppose a new feedback mechanism is identified through a diagnostic analysis, how will it be incorporated into a numerical model? Will it be automatically taken care of by the model, or shall we explicitly represent it in the model? If so, how? MG Monos.
Suppose a new feedback mechanism is identified through a diagnostic analysis. How will it be incorporated into a numerical model? Will it be automatically taken care of the model, or shall it? Yeah, there are two very good questions, Manoj. There are two ways to do it. I don't know. Let's say, for example, there are certain things a model should be able to take care of itself. But if there is something which is not coming into the purview of these equations, then probably we'll have to hard code it. We'll have to go inside the model code and change the code and use additional equations, as I said. So these kind of let's say, for example, there was some recent thing that aerosol effect. Okay, so model should take care of its own. Only thing is you have to tell model the aerosol what kind of refraction it is taking. So there are certain additional information you may have to provide to model. Some feedback mechanism which you have not given to the model, you have to tell model that what kind of feedback is probably going to happen. Especially in current scenario, in a changing climate, this probably is very, very relevant what he has. In a lot of new aerosols, lot of new pollutions are coming into the pictures, into different kind of aerosols, different kind of dust particles are coming, and these are not part of our chemistry. So aerosol chemistry should be modified. Suppose probably Dr. Rohini knows better than us, but if there is new chemical reactions happening, for example, some different new sulfur dioxide kind of composition, new particle are found, new gases are found. So those we have to change into the model inventory. That also can be part of boundary condition. That can also be become a initial condition, important of initial. For example, this case of air pollution. So we want, if we want to forecast the the air quality, we need to have this real-time observation of these that all the sources of emissions. So those sources of emission we should incorporate in our model. We should have very well coded into the model chemistry. Then only we can forecast. So what Manoj is saying, if we know some new, we come to know about some new feedback mechanism. Some methods are there which can already take care, but still we have to tell model. So these models are, as I said, these models are nothing but you and I are they are our slave. So what we have written it, we want them to perform certain tasks, they are doing it. You want them to give some you want them to do some additional tasks, you have to tell them additional instructions. So you need to give them additional instruction for sure.
I think I'm just trying to
Yes, please.
understand that. If it is not in our scale, we can do the parameterization. In that way, we can incorporate the feedback mechanism.
Correct.
But, yeah, maybe this is one of the answer.
Correct.
Yeah.
I forgot. Swagata is an expert as well. I
Thank
forgot.
you.
Sorry.
Yeah.
This was something I should have passed to him.
Yeah. So Anush asks regarding the indigenous and numerical weather prediction model. Does India have any? If yes, can you please mention it, sir? I have seen collaborative model like India Met Department GFS.
Okay, so very good question, Anush. I think developing a model is not a easy task. Number one, it takes years of hard work, not by one person, but the group of people. So, for example, you need a computer science specialist, you need a meteorologist, you need atmospheric scientist, you need chemistry expert, you need from the civil engineering background. So, several people working together for several years develop the model. Number one. So what happens whenever when the US started developing their own spectral model, which NCEP is using nowadays, it was initially borrowed by Canada. So RPN Canada at that time name was the Canadian thing, that was a spectral model back then. So similarly, when we started, when did we start? I think sometimes during Monsoon mission 2000, probably 8 or 9. Then we during under the Monsoon mission, Professor BN Goswami was at that time, I think, IITM director. That time Monsoon mission started. So that time we borrowed this model from NCEP, and IITM, NCMRWF, and Ministry of Earth Science decided to develop this model for Monsoon for applications. And a lot of development was done in this model. For example, Indian Institute of Tropical Meteorology has made changes in the physical parameterization, grid structures. So this is one model which is TCO grid. Those who know, it's a variable resolution grid which is zoomed over India, and it's a very good model. And we are operationally using it at IITM as of now. IMD is also using their own GFS, which is basically supported by NCEP at back then. But in development, all the research and development work done by MOS organizations, and then we pass on this model to IMD for operational implementation. So yes, I would not say that we have not done it, but it will not happen in 50 years. In 5-10 years, it will take another 50 years to. You can proudly say that is totally developed from India, from scratch in India. It'll take 30-40 years.
Thank you so much. Maybe the rest of the question you can answer briefly. Still many questions are arriving.
Rohan, Dr. Ira,
Rohan
I think
Mondal,
she is my former colleague. I think I would like to answer what.
Okay,
what
thank you.
Thanks,
Bias correction.
Yeah.
Bias correction required to make on every model outcomes, or we can perform monthly or yearly average bias corrections to improve model accuracies.
A very nice question, Rohan. Bias corrections are important. Bias correction are very, very important, especially when you are using for certain variables, for example, temperature and those fields which are uniform field. So models do have systematic bias. rainfall is a field which is, I don't know, I still some people do, some people don't do anomalies, especially in climate scale. People believe in anomalies, but certain variables, for example, temperature becomes very important in winter season and summer season. And if we have done systematic bias correction, it can certainly lead to a far better forecast. So yes, bias corrections are important. Bias correction should be done, and we are also doing bias corrected forecast, especially for temperature and other variables. If I remember well, I think IMD is issuing multi-model ensemble bias corrected. Yes.
Yeah, I think true. The more challenging is the rainfall bias correction.
Yeah, exactly.
Because it's a Dirac delta type of character. It's not.
Yeah, because not only that, I think it is models because of the double penalty problem. The problem is a very well-known problem actually in numerical weather prediction. What happens? Your rain is happening at a wrong place at wrong time. So, for example, in reality, it is raining in Delhi, but your model showing rainfall in Haryana at half an hour later or half an hour before. So, what happens? Your skills goes south, completely wrong. So this, it does not mean model was wrong. Model tried its best, but it got shifted in space and time. So that kind of problem is very difficult to get the biases in, especially in rain. Temperature and other field which has a uniform field, it's very easy to get biases. Here it is very difficult because one case it is going to show higher bias, one case it is going to show negative bias. So it's kind of, I don't know, maybe still people are doing. I'm not saying people are not doing. People are doing, but how reliable it is just a matter of question, I think. Dr. Ira is asking about urban planning. How can atmospheric dynamics help urban planners design climate resilient cities? Yeah, it is very important. Urban meteorology has, taken, nowadays very, very important. India Ministry of Earth Science has a special eye flows, kind of system group of modeling, which issues forecast for metro cities, Mumbai, Calcutta, Chennai, and now I think they are going to do for Bhubaneswar. Delhi has, there are many groups working for Delhi as well for air pollution and air quality, and especially hydrology related. I think ITM has started using WRF hydro. I've seen some initial results. They're very interesting. So this is very, very important. Urban planning is probably part of other group, but for we can certainly provide input to planners, especially for climate, hydrology, and atmospheric science point of view. Yes.
So next question is from regarding a simulation. Can the simulation of surface current also improve the salinity and temperature?
Yeah,
If yes,
why
how?
not? Yes. I think if I know very well. I think we are only assimilating temperature, salinity, and CIs. Currents, as of now, we are assimilating or not. I have to see, because currents are not available. I have to check, but it will certainly improve, because if the currents are better predicted into, better assimilated into the model, that will certainly lead to the better flow of the water at the surface. So that will, especially in the coastal areas, and especially in Bay of Bengal, where the fresh water plays a very, very, very important and important role. It certainly is important. I'll have to see.
Dr. Fahad Rasul from Pakistan, how a smoke incidents and disappearance can be computed or estimated, especially in cross-boundary context.
1 minute.
Pakistan and India.
Akhilesh, did you reply your previous colleague's question?
Dr. Ira?
Yes,
he was asking about urban planning. Am I right?
Yeah. So did you reply?
Yeah, I said.
Okay, I missed it. Okay.
Yeah, I think smog incidents. Dr. Rasul from Pakistan. Yeah, the smog incidents and disappearance can be computed or estimated, especially in cross-boundary context in Punjab or Pakistan. Yeah, I think this season it was I think just before Diwali, there was a storm formation in Bay of Bengal. So what happened? The winds were easterly. So instead of having bad air quality in Delhi, all the bad air quality was in the Lahore. Pakistan was facing severe air quality issue. I think 2000, I heard somewhere 1200, 1500 air quality index. So yes, this is something beyond boundary meteorology, and this is It does not know the the political boundary of this our setup. But yes, I think what your question is, I think whether we can compute. Yes, we are computing, and not only that, it was also forecasted. Many air quality models have forecasted. So the moment the storm effect was slowed down, I think the easterlies reversed, and the prevailing westerlies started polluting Delhi NCR. So it was expected. Was just it was few days. It was very bad in Pakistan, if I recall well.
Thank you. Kanchana asks, could you please explain the possibility of giving prediction correctly for an island?
Yeah, then now when you say island, whether it is Costa Rica, which is not is so small. I mean, this is very important. We can certainly issue forecast for island, but with this island is what? Is this a small island or big island? If it is a small island, very challenging. It's very challenging. I remember when I was in Florida, I think we were working for Costa Rica is one small island country in Caribbean, and most of the climate models, CMIP models, it was ocean there. They were not having land point in that grid, so they wanted to have a climate projection. So we use the regional climate model. We dynamically downscale most of the CMIP 6, CMIP 5 at that point of time, and we provided them 50-year, 100-year projection. So yes, it is possible. It certainly is possible, but how accurate it is, and there are different ways to do it. If it is a big island, for certainly it is already being provided. If I am not mistaken, many island in Andaman and other places, IMD does provide forecasts, Lakshadweep and other places. And in Caribbeans, I remember many national weather services are providing the forecast. But it is challenging if it is a very small island. Yes, for sure.
Great, thank you. Mr. Deshmukh, again asking, any artificial intelligence tools using for prediction, and if possible, will you please share some demo in the class?
I think India Met department is certainly testing, and there are many. In fact, we are developing some very useful AI tool, which our Prime Minister is very much curious that farmers should be helped, especially with this forecast. And farmers farmers are from different economical background. Some of them even don't have smartphone. So how would they be helpful with the weather forecast? So the Ministry of Earth Science is working on developing some kind of system, so that anybody from any place in India will call just using a very old style phone in a different language. System will pick up the the thing, their location, and they will provide not text, just the voice message in his own language. So that kind of work is ongoing. Hopefully by next couple of years we'll have it operationalized, and people will get their forecast at their place as and when they want.
Yeah, excellent. I think it will be very helpful. Anna is asking, how significant, almost we are end of the question, 2-3 is left only. How significant is the research on atmospheric boundary layer in view of climate system?
Oh yeah, very important, especially this in a time when air quality becomes very important. And I think Dr. Swagata and Dr. Rohini would agree with me. This boundary layers are least studied. We don't have much observation beyond, surface. We have hardly few observations. So we need more and more boundary layer towers. We need more and more, the flux towers to study boundary layers. And that's, I think government is planning to invest Mission Monsoon through Mission Monsoon 2,000 crore. So we are improving our observational network, and I hope all countries in the world should focus more in observing, because weather, unless you observe, you cannot forecast. First, you have to observe well, then only you can forecast. So boundary layer is very important part of our human ecosystem, our earth system, and unless it is understood, unless it is properly observed, we will not be able to forecast it very well. And especially from climate point of view, it is certainly important, certainly very important.
Excellent, thank you so much. Dr. Jabaid Andrabi, is there any relation between geophysical wind and albedo?
Geophysical wind and albedo. Anybody
Forward
can help
answer
me?
yes. Straightforward answer yes.
I'm sorry, I probably is Dr. Andrabi is asking from different perspective. I'm not able to follow, but yes, albedo is certainly responsible for wind flow because that creates the low pressure, high pressure system, and that generates wind. What else can I say? I mean, as per my understanding, this is
But
what
what
I
is
understand.
the
Yeah, I probably I am not able to understand properly, or maybe he wants to put it in a different way. I think geophysical winds are what? Geostrophic wind? What do you want to say? Maybe that's all. I think Dr. Andravi can write.
Okay, maybe one or two small question is left. Just
Sure.
what are the step or method for upgradation for a good or accurate forecast? One. Another is what is the difference between initial boundary value problem?
So first, I'll ask second question. I'll answer second question. What is the initial boundary value problem? Initial problem? Initial value problem?
Yes, initial and boundary initial value problem.
Okay. So let me give you an example. I normally give this example to students. I don't know, probably the question is coming from students. So you are a student, you have studied from home, you're going to your school, your daily going school, coming back to home, then going school, coming back to home. And then after certain point of time, you go to the college and you permanently go and stay in hostel and stay there and start doing your higher studies. Now, until you were going school, your initial condition was your values coming from your home, your family. But when you went to hostel, your boundary conditions become important. Boundary condition means your friends, your the circle you're interacting, and they were actually influencing you. They are influencing you more because you're away from your parents, you're away from your family. So the boundary conditions is that. Whereas on the during the school days, you were going to school, but you were coming back to initial condition. You're coming back to your home. So now the same way, if I say weather forecasting, when you're forecasting for 5-day forecast, 6-day forecast, initial condition, where do you start? Of course, these equations, if you see, they are time derivative. Means if you know the state of the atmosphere at t equal to 0, you can tell that the same variable at t equal to t plus something, some number. Okay, 24 hour later, 48 hour later. So the time derivative, if you are using the value accurately at t equal to 0, you can certainly tell better forecast. But if your initial value itself has error, so then the forecast will have more error. So it does not mean that all the better initial condition will lead to better forecast, but without better initial condition, you cannot have better forecast. So that is why numerical weather prediction is an initial value problem. On the other hand, when you're running for climate model, so you can what becomes more important in the climate model. Climate model does not have boundary. First of all, it is a global model. Normally, they are having an ocean and atmosphere model, and what impacts them is surrounding. What is the boundary condition is how the aerosols, how the gases in the atmosphere, how the greenhouse concentration of greenhouse gases in the atmosphere are changing over the period of 50 year, 100 year. So that's called boundary value problem. So that is taken care. That's why climate modeling is considered as a boundary value problem, whereas weather modeling, numerical weather prediction is considered as initial value problem. I hope I answered that. I forgot what the first question was.
Okay. First question is what are the step or method for upgradation for good or accurate forecast?
So yeah, as I think I have already answered this. A step or method to provide the accurate forecast is you should have a better assimilation system. You should have a good assimilation system. You should have a good modeling system. So that will lead to certainly a better forecast. You should also have a better computational resources as well. So depending on what is the uses, what are the applications, what do you want this model for use for?
Okay, just I think we can take one question from the YouTube. Maybe that may be the last question, or maybe one more, if Rohini allowed.
No problem.
Okay, so Punna Durga asking, is spectral models used for horizontal resolution will it improve weather prediction?
A very good question. Spectral models, that what is and good thing is in a spectral model, they require less computational resources because they don't solve equation on each grid point. The whole energy is solved in a spectral domain, and then it is transformed into the grid. Now the interesting thing is there is a limitation to a spectral model. There was some study which tells that, which was elaborating very nicely, that if you are running model more than 10 kilometers high resolution, means basically if you go high resolution compared to more than 5 kilometer, 10 kilometer, then spectral models become irrelevant. So if you are running coarser resolution, that's why you see all the climate model earlier time, they were mostly a spectral model, because they were very coarser resolution, 600 kilometer, that you must have T120, T170. Those were the number of spectral waves, in the models. Those were defining the resolution of the spectral model. So for climate application, even for weather application, they were doing good job. But as the model resolutions have started increasing, compared to 50 kilometer, 100 kilometer 10 years back, now the models are running at 10 kilometers or even a single digit kilometer scale model. So kilometer scale model are not easy to run. As of now, my understanding is the physics and the science behind these spectral models as of now are not able to address that challenge, because the only advantage was it was requiring less resources and giving the solution very accurately, but which is not happening at that high resolution.
Thank you so much. I think already covered almost all questions, more than 35 plus questions you already answered with a very great enthusiasm and energy.
Somebody is asked.
Last one question is from Rajaya.
Yes.
How many ensemble members I think NCMRWF using, and also Dr. Javid gave a clarification. First, you can answer the Rajaya's questions.
Okay, so number of ensembles in NCMRWF global forecast system is 23. So 23 ensemble, 9-day forecast. So we are issuing every day. And
Excellent.
Dr. Javed Andrabi has said wind can stir up dust or sand. There is a relationship between geophysical wind and albedo. Wind can stir up dust or sand, which can change the surface parameters. Yeah, perfect. You have absolutely right, sir. I think I was taking your question in the context of my presentation, which was not fitting in some, unfortunately.
Yes.
Sorry, I misread your question. So your is much more generalized, question and much more generalized answer. Very good, very good. Thank you very much. I'm sorry about your, I'm not understanding your question.
Okay, I think you can share some of your publications or your some model paper. Some attendees are very much interested to go through on it.
Sure.
So,
thank you.
Yeah. Thank you, Dr. Akhilesh, for your excellent and energetic reply with great knowledge. And thank you, moderator. Over to you, Dr. Rohini.
Thank you, Dr. Mohan. So thank you, Dr. Akhilesh. Before we go to the vote of thanks, which will be given by Dr. Swagata, I would like to tell that almost around 250 participants have attended this session, and more than 205 participants have rated it as excellent or very good. So we are very happy that participants are taking interest and they are trying to learn more and more. So this is really nice, and your explanation, definitely your questions and explanation was really very good. So thank you very much, Dr. Akhilesh. So over to you, Dr. Swagata. I will just share the screen for vote of thanks.
Yeah, also before coming to that slide, I really want to say big thanks, because a long time I was thinking the presentation should be small, the discussion time should be longer. This is the first time. This is the first time.
First time it has happened.
The presentation was less
and the discussion was 40
much
minutes.
longer. So I am very happiest today. Yeah.
Thanks to Professor Somnath. I think he gave me a lot of background, so I didn't have to do work on the background. I think that helps actually. I hope future presentations would be like that. Interaction is important, certainly.
And this is a subject where we feel that, okay, I think we miss the spin up. I think we the regional word, that's why boundary word coming in. I mean, a lot of things still are there, and we'll cover day by day. So, on behalf of the organizing committee, I extend my heartfelt gratitude to each one of you for your contribution for this third lecture of weekly online lecture series on atmospheric dynamics and its application to climate sciences. Firstly, I would like to thank Air Vice Marshal Professor Ajit Tyagi sir, President SAMA, for giving welcome address and brief information about this lecture series. My deepest appreciation goes to our speaker of the day, also our friend, our alma mater, a lot of XYZ, Dr. Akhilesh Mishra, scientist and project director, Monsoon Mission, Phase 3, NCMRWF, for delivering wonderful and very informative lecture on vector equation of motion in an absolute and rotating frame of reference. I also thank to Dr. T.V. Lakshmi Kumar from JNU New Delhi for introducing our today's speaker, Dr. Akhilesh Mishra. My heartfelt thanks goes to Dr. Mohan Kumar Das for nice conduction and untiring to do that question and answer session. My sincere thanks goes to Dr. Rohini Bauer, the program convener, for moderating today's session, always with a smile. Finally, I express our heartfelt thanks to all the panelists, participants, and attendees who joined us from across the globe. Your presence and active participation plays a key role for the success of this lecture series. So please continue. Last but not the least, I want to thank all the students and scholars of Savitribai Phule Pune University for their support in organization of this lecture. Thank you.
Thank you, Dr. Swagata. And I think
Rohini,
yes, sir. Sir, please.
let me also compliment both the Akhilesh and all the participants who have put very, I'm say, it's not just for the sake of they were asking questions, they were very insightful, and equally good were the response. And I'm really happy, and let's see that this is kept in subsequent lectures also. May I request you to keep record of that, how many long sessions, question answer sessions are there, and we may acknowledge their contribution also.
Yes, sir.
Yeah, so that is very important. Success of this series is in the question answer session, and this was excellent. So Akhilesh, good show. And equally important are the participants who and the Mohan who coordinated this session very well. Okay, all